Excellent. Thank you for coming for my talk. Some of you have seen my talks before, things like, oh God, my brain, or whatever I called it at the time. I got some feedback, maybe be a little bit gentler to people and just put less in. I tried, is all I'm saying. So let's get going. All right. We're in a typed functional programming language. We're solving some problems. We can use our types to model our problem and help constrain our problem space, and then we can be creative inside those constraints. Sometimes what you really want is a heterogeneous map. Not a map of all the same values. You want to mix things up a little. And then you don't have one, because a lot of the solutions are terrible. And so if you're doing a health-related thing, you do something like this, where you put a bunch of stuff together, and you hope for the best. And if we had a heterogeneous map, we could deal with all these things fairly uniformly, but instead we do this kludge of things and hope for the best. All right, we're going to improve on this. Our first way of improving things is put functors everywhere. Hey, like this. We put a little f parameter in, and we put it out the front of things, and then this gives us a little bit more flexibility. It allows us to do things like, if we use the maybe functor, we can have this data structure with a whole heap of holes in it. Like if we're filling out a form, the things that haven't been filled out yet are nothing, and if they've been filled in, they're just. And then we can go through and kind of wrangle it and say, if everything is filled out, I am done. Here is one where identity is in all the places. Otherwise, you've got nothing. And by changing the functors in those spots, you can get all kinds of funky behaviors. Not very pleasant yet. All right, this is all kind of like an overview of what's to come. If we had the functors in, it's like, I haven't got enough extensions turned on. So we turn on some extensions. All right, GADTs are the first one. So to get towards this heterogeneity, we want a key type that also kind of hints about the values associated with the keys. And so we use GADTs to create a series of keys tagged with the values they're going to be mapped with. And that's where Dmap comes in. So here we have a Dmap of those keys, where each key is mapped with its corresponding value, and it's wrapped up in an identity functor as a bonus. Wrap functors and everything, because that's probably a good idea. Now, it's in the module data.dependentMap, but all of the source code originally came from data.map. Copy and paste, sprinkle over these extra superpowers. So all your operations are nice and efficient. So it's basically just a fancier version of data.map. Cool. And we can do form data. We can deal with all of our keys effectively and uniformly by traversing over things. Yay. I can look down here. That's good. And so we can do our check everything is filled out thing with a simple traverse. We can tag all of our errors and have them so they map to the keys. So rather than just saying something went wrong, here are the things, we can say something went wrong in this field and this other thing went wrong in this other field, and you don't lose that information, the provenance of your errors. And then we can just run wild. We write a function that does stuff with functory things and effects, and then we just jam it into a Dmap. And we'll get to all of that. But first, I'm going to back up and explain GADTs and roll through all of these pieces. So that's the trailer, and this is the talk. So this is a regular Haskell type. We have details for some patient with their initials of date and birth, or they're already in the system and they have an ID, and we just treat them like a number, because that's health systems, right? Each of these constructors has a type. Patient details takes your initials and your date of birth to create a patient information. Patient ID just takes the ID. Not really called out so much. If we turn on GADTs, we explicitly give type signatures for all of our constructors. So far, so good, not that much of a step forward. But there's all these little type tricks that people play that give you good things, and they play very well with GADTs. Phantom types are one of them. If we want patients to start off, we gather their details and then we put them into the system, we can create a couple of types. They're a new patient or they're in system, and tag our patient information with that type using the A type parameter. A is never used inside the values. It just separates our types out. And then we export our smart constructor saying a new patient is a new patient. which makes sense. And then when we're adding a patient to the system, we can pattern match on our patient details, grab everything out of that, put it into the system. Oh, but that's a partial function, and so we pattern match on the thing that we're never actually able to construct. And in this case, we're lucky enough to just be able to return it, and it matches up, but otherwise we'd have to do some garbage or error or whatever, and it's bad. With GADTs, because we're writing out the types, we can type out individual constructors, so the type system knows that your patient details are for new patients. And then, when we pattern match, this is the only thing that we have to pattern match on, because the type system knows patient information, new patient, only has the patient details constructor. Yay, type information is flowing. And that is great. We can smuggle other things in. So if we have for alls and constraints on the right of an equals, we can kind of put some constraints on that kind of get carried around with us. So we can smuggle those things into our patient details. So this is advanced serialization. Show A, read A. Woo! For putting images or random stuff into our patient nodes. But it's enough. When we pattern match, the show falls out, and we can use that to write a show instance for our patient details. The GADTs, we can also do that, but we can scope it a little bit more carefully, which can be nice and comes up later. And then we've got something a little bit like in Bartos's talk, where we can pattern match on these to learn new things and then construct things to capture evidence. So this is type equality. We're saying A is equal to B if we can construct it using REFL. You met a version of REFL this morning. This is non-dependent, easy mode REFL. If we have a look at, if we break a case on AB, then we get evidence that A is equivalent to B, because that's the only way it could have been built. And then we match on B is equivalent to C. And now the type system knows that A and C are the same thing, and so we can capture it. So that's moving evidence around a system using GADTs. All right. And then we can just go nuts. So we can write a little AST language where we have ints and bools and functions between ints and bools and other functions, and nothing else is expressible. You can go a little bit crazy with this. I'll probably reference this a little bit later, but you don't need to remember it. And you can do just stuff. This is just nothing up my sleeve. You don't need, there's no test on this. The functor pattern, we cover this, and then things get started for real. If we have some patient details, and we sprinkle Fs everywhere, then we're using the functor pattern. We can write a generic map over details thing that takes a natural transformation as like a higher order functor, and then transforms all the bits. And we can use that to write our, take patient details and drop it back down to maybe, so we can put it in a form for editing, which just maps over everything, runs the identity, pulls the identity off, and puts the just constructor on. If we want to add an effect in, we can write once and for all traverse for details, and then we can use that to do our now kind of slightly repetitive check everything is filled out example by just traversing over it and pushing the identity constructor through the just. Trust me, there's, again, no test on this. But then we can get a little bit inventive and think, well, if we're playing with effectful natural transformations, let's just put them in a new type and see what happens. And this is a way of giving us a different effectful natural transformation for each field of our details, and we can package it up. Why might you want to do that? Well, we can write validators for all of our fields. So this is just, the initials must be set and must be greater than 2 in length, otherwise you get errors. And we can package all of our validators together, and that totally fits inside one of these things. And then, because we can apply those functions effectively, and we have them all packaged up, we can just write something that validates patients by applying all of those effectful functions to our information. Benjamin.pizza, I don't think pizza is his last name. I think it's just a domain name that was available. Has a great post on this. And if you Google functor Benjamin pizza, the post will be summoned. And yeah, it's a good read. All right, Now we're getting into the Dmap-averse. I found this through the Reflex guys who use this a lot. James Mokus is his GitHub name, came up with it originally. We start off with dependent sum, just to warm up. It's this thing. We have some key type, which has types associated with each key, and then we have a functor full of those things as values. An example will help. Here are our keys. Our patient information is either initials and a date of birth or an ID, depending on which way we build it. We're going to package it up into a dsum so we don't have to carry around these ints or text or dates of birth. And so here's a dsum of patient details in an identity thing. And we're not talking about the ID int thing, because that's hidden from us. If we have applicatives, we don't even need to say identity. And when we're using it, we can just kind of pattern match our way to victory. So if we have no details, we can freak out. If we do have details, we can put the patient into the system. If we don't have an ID, well, maybe we shouldn't be playing with IDs, but we freak out. And otherwise, so by pattern matching, we have the type information of each of the key value pairs available inside of that pattern match, and we can do things with it. To use this, we have a few type classes that they kind of add into the mix to make it usable. So to compare keys where the types might be different, we have this GADT equality type for keys that captures evidence that two keys are the same. And you could write it out using the usual pattern, if they're the same, then they're equal, otherwise go away. And there's a comparison type that's similar, and you follow the usual patterns for writing comparison. And don't ever do this. Show lean on template Haskell. So I'm just telling you these classes exist, but what you really want is this. Hey, and now you're cooking with gas. You probably also want this, and it's going to come up later. If you're using GADTs, you lose the usual deriving at the end, but you can use standalone deriving to get your usual type classes you know and love. And yes. And there are some other classes that you'll see in type signatures, or if you look at the current code, but they're kind of going away if the Reflex people have their say, and I'll show you why later on. I'll show you why. All right. Eek. So this is the equality kind of thing for comparing your values when you have key information to guide the types. And yes, you don't need that anymore. I will show you how. On to the star of the show, Dmap. We have our key type, we have our functor, and then we have it creates a partial dependent map by just copying data.map and adding this extra type information throughout it all. We can go to and from lists. Like the API is basically the same, including some copy-paste errors in the Haddix that don't refer to the extra type information because they just went through it from start to finish. You can insert, delete, like when I say it's the same API, it's like very much the same API. Unions, handy. Differences, handy. Intersections, handy. And the reason they're really handy is that this is kind of forming an extensible record system, and being able to do efficient unions and intersections and differences becomes really important when you want to lean on one of those things with thousands of fields being combined in weird ad hoc ways. The things that I'm leaning on in this talk are you can map maybe to filter things out, and you can traverse to do effectful things, because that's where all my good examples come from. All right. So here's my patient details in my extensible record system via dependent map and sticky tape. We have our initials and date of birth, we have an optional weight, and we have another dmap inside the key for existing conditions, all wrapped up in a functor. Because it's a partial dependent map, sometimes we start things off with like, here are all the keys that you would like. So you can create, this is my empty form for start with these fields. There are other ways of dealing with this. And then we can traverse over that to check the form is filled out, or map over it to take a record and prepare it for form worthiness. We can take our validation stuff from before and our validation functions from before, and then we can build a Dmap of validation functions and then do stuff. Don't look too closely at the code. There's a point I want to make here in the abstract, and part of it is the code is ugly. This is all evolving, so we're doing an intersection to run the validators, and then we need to do a sequence, and they don't have sequence yet. So we have a traverse with our fmap identity to kind of like just quietly fake it. But yes, I'll do some PRs, and everything will be fine. Yeah, we can change our error type a little so that we actually have provenance information, so we know which errors are occurring which keys. In a form validation library, that's really nice, because then you can automatically just display the errors in the right spot at the cost of 5 tokens. Yes. The thing that you'll probably play with the most, because the usages and best practices are kind of still slightly emerging, is you could start with that map of all the important keys with nothings in them to kickstart your form, or you can start with dmap.empty, and then really lean on your data.map skills to union and intersect your way to victory. In this case, we're assuming that we have an object with things in it, and then if you look down the bottom, I do a little bit of union stuff, and then that can handle the case where you start with an empty map, and we're kind of just validating the thing we have validation functions for. The main thing I'm pointing out here is that you'll have to find your own feet with those things a little until some more patterns get codified. But it's just the same as playing around with data.map rather than a usual like vinyl or some other extensible record system. Cool. There are tricks with keys that are good to tell people about. The first one's just a cute little GADT. You can capture up all of your keys and talk about them uniformly. This sum constructor drops the A off a key A. And so if I've got some map and I ask for the keys, it can tell me in a uniform way. I just find it cute. Actual productive tricks with keys, we can nest them. So before I had my new patient and my in-system versions of patients. Here I've treated these keys like they're going to become extensible records for each of those constructors. I can create a new key that passes them along, and it's kind of encoding that union in the type level. It makes it pretty efficient for me to filter out and say, hey, give me all the ones that are new patients, because I can just check for that outer wrapper. And I can promote things by just mapping over the keys and putting the wrapper on. The reflex guys use this a lot. It's kind of handy. And we can do weird things to check for that. So a map full of proxies is a way of saying I'm interested in these keys without having to come up with values. If we intersect a map with a map full of proxies and we get the map full of proxies out, it means all those things were present. And then we can create it. The point is, you can create a test object and say, hey, are all these fields present? And it's a couple of lines of code that you can reuse. All right. We can do slightly better. For those who are aware of classy prisms, you can write a classy prism for your key type. There are other extensions in play here, but that's fine. A little bit of plumbing. This is more or less like handwriting what you get from the template Haskell for creating classy prisms. And once you've got that, ignore the man behind the curtain, you can wire it up fairly easily. And then we have a generic test object. Anytime we have one of these prisms, we can say, yep, this has the new patient fields. And then we don't have to blindly follow the reflex best practices and build our unions into our types in ways that we may not want to. We can just write more and more prisms and just write the keys we want. So that's something I've been playing with. I know some people like classy prisms, so I put it out there for you all to play with. All right. Yes, that's what I said, slide. All right. Now the dynamic bit. Sure, we've got keys for all of these things, but what about the keys you're not expecting? PrimUnique is a package in this universe that has your back. It has a tag type, where the A is a phantom type, and you have all of the instances to work with dependent map. How this plays out, I'm going to create patient notes. They have a time, and they have a thing. And the thing has eq, ord, show, and read, our advanced serialization platform. and we're just going to have a big map of these nodes. So when it comes to adding a node, we grab the time, we create a tag with at the moment it's going to be tagged with A through its usage. We have no idea what A is. But there we go, we've just put it into a map of these things. And when we're using it, I create my empty map, I'll add an int. Why not? And I'll add a bool, and later on I can, without recompiling this, I can add all kinds of types that I haven't even created yet. And then if I print it out, it works. Magic. That's the delightful dynamism. Sometimes a bit too much magic for people who see it the first time, but if you click through the slides on slow-mo afterwards, it might make more sense. So to get away from like wizard magic to ed magic, the last little trick that gives you good behavior with constraints is using the constraints in constraints extras package. And we're going to use this to write a show instance for dsum. So we have a key, we have a functor, let's show it. Or let's think really hard about how to show it, because it's not really obvious what we're going to need. This involves plumbing, and this kind of plumbing involves type classes, so we reach for the constraints package, which gives us the ability to capture a type class dictionary in a dict constructor. And then we can use it later using withdict. If we've captured a type class in dict, and we have a computation that requires that particular type class, withdict lets us run it. So if we have an equality for x and some function that requires equality for x to give us a y, and we're in some module where we cannot get hold of equality for x, we can smuggle it in using withdict. Because dict is a data type, we can put our dictionary with equality for x into a record somewhere and pass it through our program and then just pop it out using withdict, which is pretty cool. And there's other plumbing things in constraints. This gives us entailment. If you've got ordx, you've got ekex, and then we can kind of use it. So if we have ordx, and then for ekex, anytime you've got ordx and a computation that requires ekex, this will bust things open and rummage around with them to give you what you need. You don't need to remember this. This is just flavor of constraints has combinators to let you do type class passing around plumbing stuff. And it's less scary than the stuff that follows. Do not be scared. Just follow the intuition. I promise it will all be OK. When we have for alls in play, constraints has this for all f thing, and then whichever is the combinator from constraints extras to use it. What happens is, when we said, give me a show for details key A, we got a for all f show details key. The for all captures that A. And then if we have for all f show details key, it means that for each A, we definitely are able to access show for details key A. So dsum, provided we have for all f show k, which we do from our deriving, we can use whichever to bust out the type class dictionary for ka to show it, and then show it in those brackets there. And we're 2/3 of the way done. Oh, and then we've got functors of A, where the A depends on the key type. So we dig further into constraints extras. Do not look at the thing on the top. Template Haskell, your friend. Derive argdict, and then something happens. Look at it later, but do not look at it now. Once you've got derive argdict, then everything is fine. We end up with this has constraint, which looks like this, ugly combinator. Just defocus your eyes somewhat. The intuition is, if we've got the constraint has show details key, it means for each details key A, we have show A. Argdict has captured that for us, and this will bust it out. And then if we want to wrap that in functors, has prime is the same thing, but for f of A. And so has prime show details key f means that if we have details key A, we definitely have show f of A. And in this case, that just means we need to put in has prime show kf, and we can use has and the key to select the right dictionary, and we can do all of this. All right, I'm going to speed up a little because this actually leads somewhere. The mad folks at Reflex went further with this in the extensible record story and built something called Vessel, which is young and growing. It's built around this view type class, which gives you, its whole excuse is condense and disperse. This is its reason for living. You send them a web request. Probably other people send them web requests at the same time, so you'll have a map of requests. Condense lets you flip that around. So you go from a map of requests to a request where each field is wrapped in a map. And then if it's a request for data, for every field where the map is not empty, you can grab that from your database. But for everything else, you can leave it alone. And once you've done your single aggregated request for data, you can use disperse to scatter that information back out to who asked for it. They love it. It gives them some kind of Haxel-style aggregation of querying, and it's pretty cool. It also gives them intersection called crop for historical reasons, and our usual mappy, traversey functions. They have a whole heap of building blocks that have view instances. If you want to put one thing into your extensible record system, it's definitely there, identity V, V for view. One thing that might be there, single V. You can use maps, you can use dependent maps, and then you get my highest kinded type in the expression, in the talk, Vessel, which has blah, 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 and a G for a functor. And Vessel has a view instance if every key has a view instance. So you can stack all of these things together and get all of that nice behavior. What does that look like? For patient details, definitely have initials. I definitely have a date of birth. I might have a weight, and I have a DMap of existing conditions. And now I have condense and disperse and map and traverse for all of those things. As long as it's got the missing functor parameter at the end, I can put it there, which means I can put vessels inside of vessels, if I am that way inclined. Has becomes has-v for their weird type juggling stuff. And then we've also got this. If I can compare keys, and if I can serialize the keys, and for everything that has it, for all of my key types, I can also serialize them, then I can serialize vessels. So I do a few derivings for my bits out of the leaves, and then I can stack them all together into an extensible record system and get serialization effectively for free. Cool. And they use this for incredibly cool Haxel-like things that aggregate and disaggregate data flows. I'm using it for form libraries and weird widget things. You can get pretty far pretty fast with just what's in this talk. Yes, and it's an interesting point in the design space. I think I'm about to get crash tackled. Kale from Reflex thinks it's the bee's knees for extensible records, and I'm very much catching up to that point of view. You may burn yourself if you go too hard on it, but you can always ask me questions because things are still evolving and emerging. Cool, that's me.